Hi, I'm Hussein. Welcome to episode 6 of the Grasshopper from Zero series. In this episode, we're going to explore one of the most important and exciting topics in parametric design: patterns and attractors. Almost every form you see in today's parametric architecture is somehow based on these two concepts, from complex facades to space frame structures, panelized surfaces, algorithmic roofs, and even many of the projects by architects like Zaha Hadid or Big. At first glance, they might look complicated, but the interesting part is that the logic behind most of them is actually much simpler than it seems. We usually start with a set of points, define relationships between them, and then apply a few simple rules to generate forms that can become fully dynamic and responsive. For example, if one point moves, the entire pattern can change. If distances change, the final form also changes. And that's exactly where parametric design becomes fascinating. Section 1, patterns. So what exactly is a pattern? A pattern, in simple terms, is an organized repetition. Whenever an element is repeated based on a specific rule, we are essentially creating a pattern. This repetition can be very simple, like a series of squares placed next to each other, or it can become much more complex, like the patterns we see in nature, the structure of leaves, the surface of certain organisms, cracks in dry ground, or even the geometry of a beehive. In architecture, we are constantly dealing with patterns as well. For example, facade panels, space frame structures, tiling systems, lattice facades, or even the way columns are arranged. All of these are types of patterns. But here's the key difference in parametric design. These patterns are not fixed. We can change their underlying rules, and the entire system updates in real time. For instance, if the distance between points changes, the pattern changes. If the size of the modules changes, the whole form updates. Or if a single point starts influencing the system, we can generate completely dynamic and responsive patterns. And that's exactly why, in Grasshopper, patterns are not just decoration, they are part of the design logic itself. Before we start building patterns, we need to talk a bit more about points, because almost every pattern in Grasshopper starts from a network of points. In a way, points are the foundation of our entire system. Everything else is built on top of them. We can create circles from them, draw lines, generate surfaces, or even control an entire structure using just points. For example, if we want to create a triangular grid, a Voronoi pattern, or even a parametric façade design, in the end, we always need to know exactly where each module is located. That's why in this section, I'm going to show you a few very important components that help us generate different types of point networks. The first command is rectangular. It's one of the simplest, yet one of the most important tools in Grasshopper, used to generate a regular network of points. Instead of placing points one by one manually, this component automatically creates an organized array of points for you. We usually use it as the starting point for many patterns, paneling systems, facades, or parametric structures. Inside this component, we define the number of divisions in the x direction, the number of divisions in the y direction, the spacing between each point or cell, and the output is a clean, regular grid of points that we can later use to generate surfaces, build patterns, or control geometry. For example, if we want to design repeating panels on a surface, the first step is usually to create this kind of grid. The important thing is that rectangular grid is not just a simple layout tool. It's actually one of the fundamental building blocks of many parametric systems in Grasshopper. Because when your data is structured and predictable, controlling the form becomes much easier. Populate component. The populate component is used to automatically distribute points within a given boundary. Unlike a grid, which places everything in a perfectly ordered structure, Populate spreads points in a random or semi-random way. That's why the result usually feels more natural and organic. For example, if you want to define the location of trees in a site, create a perforated pattern on a surface, or generate a non-repetitive pattern, Populate is often the better choice. Now, Populate comes in different variations. Populate 2D distributes points within a two-dimensional region. For example, inside a rectangle or a flat surface. You simply define the boundary and the number of points, and Grasshopper generates the distribution automatically. But Populate geometry goes one step further. Instead of working in 2D space, it generates points inside a 3D volume or geometry. So you can fill a box, a volumetric form, or even a complex architectural model with points. The key difference between Populate and Grid is the type of order they create. Grid is based on repetition and structured arrangement, while Populate is based on randomness and free distribution. And interestingly, in many parametric projects, it's the combination of order and randomness that creates the most compelling and natural-looking patterns. Discontinuity component. The discontinuity component is used to detect breakpoints or changes along a curve. In other words, it finds the places where the behavior of a curve changes. For example, if a curve has a sharp corner, or if it is made of multiple segments joined together, discontinuity can identify those points and output them for us. Basically, this component looks for locations where continuity is interrupted. That's exactly where the name discontinuity comes from. This is very important in parametric modeling because in many cases we need to understand where a form actually changes. For instance, we might use it for panel subaddition, controlling corners and edges, creating connections between elements, or analyzing the behavior of a form. What's interesting is that discontinuity doesn't only detect obvious sharp corners. Depending on the type of discontinuity we choose, it can also detect more subtle changes in direction or curvature. So we can define exactly what kind of break or change we are looking for, whether it's just sharp edges or even variations in curvature. In simple terms, discontinuity helps us reveal the hidden structure inside a curve and extract its most important points. Of course, when we step into the world of plugins, the number of tools and pattern-making techniques increases significantly. But in this episode, we're going to focus on the core components of Grasshopper itself first. Later, in the plugin-focused episodes, we'll explore those advanced tools in more detail. So now, let's move on and look at a few key Grasshopper components used for creating patterns. The Delaunay Edges component is used to create triangular connections between a set of points. Basically, we give it a collection of points, and the component automatically calculates the most logical and efficient connections between them using the Delaunay algorithm. The result is a stable and organized triangular network made entirely of lines generated automatically by the system. So instead of manually drawing connections between points, Grasshopper handles the relationships for us. What makes this component really powerful is that the structure is completely dynamic. If we move the input points, the entire network updates instantly in real time. That means we can directly control the form by simply adjusting point positions and immediately seeing how the structure changes. To create the network, we just connect our points to the input of the Delaunay Edges component. The output is a set of lines representing the connections between those points. From there, these lines can be used for many different design purposes. For example, we can use them for space frame structures, surface subdivision, paneling systems, parametric patterns, or even complex architectural forms. An important thing to understand is that this is not just a static drawing. Because the geometry is generated parametrically, we can control every individual edge in the system. We can filter them, change their thickness, convert them into pipes, or modify them based on length, position, or any other parameter. In the end, Delaunay Edges becomes more than just a tool for drawing networks. It turns into a flexible parametric system that continuously rebuilds itself based on the input data. Voronoi is essentially a method for turning a set of points into a cellular network. It divides space based on the closest distance to each point. When you run the Voronoi component, the first thing it needs is a collection of points. These points act like the core seeds of the system. Then Grasshopper calculates the distance relationships and generates boundaries, producing a set of polygonal cells. Now, depending on how you use it, Voronoi in Grasshopper has a few important variations. Voronoi 2D. This is the most common form. You place points on a plane or a surface, and the output is a set of flat polygonal cells. This version is widely used for façade paneling, pattern design, and surface subdivision, Voronoi 3D. In this case, we move into three-dimensional space. The points are placed inside a volume, and the result is a set of 3D cells. This approach is often used for foam-like structures, lightweight systems, or organic forms. The real power of Voronoi in Grasshopper is that it is fully parametric. If you change the position of the points, for example using Move, Attractor Systems, or Populate, the entire network updates instantly. Because of this, you can easily control the density of the cells, modify their scale and distribution, or even shape the pattern based on external forces. And that's what makes Voronoi not just a pattern generator, but a responsive design system. Once the network is created, we also have many further possibilities. We can apply an offset to the entire structure to give it thickness or spacing. We can extrude it and transform it from a 2D surface into a 3D volume. We can even introduce variation, for example, using random radius values to enlarge or shrink some cells while keeping others unchanged. This breaks the uniformity of the grid and creates a more natural rhythm in the pattern. The components we've seen so far are essentially tools that generate patterns for us automatically. But the important point is that we are not limited to these tools. At the end of the day, what we really have is just a set of points. And these points give us the ability to design patterns ourselves from scratch. In other words, when we have a list of points, we can define a module on each point, and by controlling the relationships between these points, we can create completely different and fully controllable patterns. Section 2, Attractors. An attractor in Grasshopper is actually a very simple concept, but it is one of the most powerful tools for generating parametric forms. In its simplest definition, an attractor is a point or an influencing factor that causes other elements in the system to respond to it. Instead of directly designing the form, we define a driver, and the form evolves based on its relationship with that driver. In Grasshopper, we usually start with a network of points. At the beginning, these points only have positions, they are just distributed in space with no specific behavior. But once we introduce an attractor into the system, everything changes. The first step is to calculate the distance from each point in the network to the attractor. In other words, we ask for every point, how far are you from this central influence? The result of this step is a set of values that represent how close or far each point is from the attractor. And here is the key idea. These distances are no longer just numbers. They become design parameters. We can use them to control different aspects of the form. For example, we can change the size of a module, control the height of an extrusion, or even define the intensity of a transformation based on that distance. Usually, before using these distances, we normalize or remap them into a controllable range, for example, between 0 and 1. This gives us much more precise and predictable control over the form. Ultimately, the result of this process is that the behavior of the entire system becomes dependent on a single point. This means that if the position of the attractor changes, the whole form changes as well. And as it moves, parameters like size, height, or density all update simultaneously. Now, to implement this in Grasshopper in a practical way, let's go through a simple step-by-step example. First, we need a network of points. For this, we use the rectangular grid component. This component gives us a set of evenly distributed points in space, which will act as the base of our system. The points output of this component is the grid we are going to work on. In the next step, we define the attractor. To do this, we simply place a point in space. We can use either construct point or a point parameter and treat this point as our influencing factor. We usually position this point outside the grid so that its effect on the system becomes clearly visible. Now we move into the main part of the definition. To understand how much each point is influenced by the attractor, we use the distance component. Here we connect the grid points to the first input and the attractor point to the second input. The output is a list of numbers, where each value represents the distance from a specific point in the grid to the attractor. At this stage, these distance values are not yet ready to be used directly in the design. That's why we use the bounds component first, and then remap numbers. First, bounds defines the overall range of the distance values. Then, with remap numbers, we map these values into a new range, for example, between 0 and 1. This process makes the data much more controlled, precise, and predictable for design purposes. Now we reach the interesting part, turning this data into actual form. Let's assume we want to generate circles from these points. For this, we use the circle component. We connect the grid points to the plane input and the output of remap numbers to the radius input. In this way, each point generates a circle. But the key idea is this. The size of each circle is driven by its distance from the attractor. This means that the closer a point is to the attractor, the larger its circle becomes, and the further away it is, the smaller it gets. If we want to take this system one step further, we can replace the circles with an extrude operation. In this case, we use the same remapped values as the height factor, and with the help of a unit z vector, we turn them into an extrusion direction. This way, instead of just changing the size of circles, the system starts to generate actual 3D variation in height, fully driven by the attractor. In the end, the overall structure of this system looks like this. We start with a rectangular grid to generate the base points. Then we define an attractor point to act as the influencing factor. Next, we use distance to calculate how far each grid point is from the attractor. After that, bounds and remap numbers are used to control and normalize these values into a usable range. And finally, we use either circle or extrude to generate the final geometry. This simple chain is the core logic of an attractor-based system in Grasshopper, where geometry is no longer drawn directly, but generated through relationships between data. The result of this process is that we are no longer designing a fixed form. Instead, we are creating a living system that evolves. By simply moving one point, the entire structure responds and transforms. And this is exactly one of the core principles of parametric design. In the end, what we saw in this episode is that patterns and attractors are not just Grasshopper tools, they are fundamental concepts in parametric design. Patterns help us build structured and controllable systems out of repetition and order. Attractors, on the other hand, take those structured systems out of a static state and introduce behavior and variation. In a way, one defines the rules and the other introduces the behavior. The key idea is that in this type of design, we are no longer directly designing the form. Instead, we define a system and allow the form to emerge from it. Everything starts with a few simple points, but once we define relationships between them and apply simple rules, the result can become a complex, dynamic, and fully controllable form. And if I had to summarize it in one sentence, we moved from designing shapes to designing systems. Thanks for staying with me through this episode. In this video, our focus was on patterns and attractors, but this is really just the beginning. Many of these ideas can be extended and expanded using plugins, which we'll definitely explore in separate episodes. In the next part, we'll move on to space frames and structures and talk about space frame systems and trusses, where we shift into a more structural and practical side of parametric design. Feel free to share your thoughts, experiences, and suggestions in the comments. It really helps me understand how you connect with these concepts. If you found this video useful, make sure to like it, and if you haven't subscribed yet, consider subscribing. See you in the next video. Goodbye.